Welcome, everybody, to session number 2 of the AI Engineering Bootcamp, Cohort 5. Today, we talk embeddings and RAG. I want to get right into it today because we've got a lot to cover. There's a lot of prerequisite material that we'll cover as well. And those of you with a less robust background in data science or software engineering might get a ton of trailheads to look down and to explore as you continue your journey into AI engineering. But first, let's see who's been building, shipping, and sharing in the cohort. We see some serious action in the BSS channel. I love this. Tomfoolery, Waleed, it was great to see you in office hours today too, my man. Philip, other Philip, and Ben, crushing it. Way to go, guys. And then, I just want to shout out as we kind of drown out the noise of the rest of the community with our cohort. It'll be harder and harder for me to highlight these, but this was some cool work from Angela, who's super legit, way worth connecting with. She's got a transformation of the week you should check out, doing some benchmarking on Anthropic's prompt caching. Everybody's talking about like prompt caching like it's kind of new, like we want to augment with caching these days. So it's kind of a cool thing to take a look at. We'll talk about it later in the cohort. And AI by AI, shipping avatars, love that. Next week, I got a question about this in office hours, actually. How do we evaluate agents? Well, we will fit it into the curriculum, even though it wasn't as originally designed. It's one of these emerging topics. We got to fit it in over the next 10 weeks, but you can check it out next week on YouTube Live. Thanks for everybody for joining us that joined us yesterday. It was a real fun event we did on LLMs. We'll talk about it just a little bit later. At least I'll trailhead it at least a little bit later. I want to tell you about Vincent for a second. So Vincent is going to be available on a weekly basis. And Vincent, to be candid with you guys, is the person who I am looking at as the next instructor at AI Makerspace. He's going to kind of be able to play some Dr. Greg role as we continue to roll out more courses in the coming months and years. And so, he's actually really good at teaching. He's from France, so he's in a different time zone. He can't quite join us. It's the middle of the night for him. I know some of you guys are staying up late, and Vincent used to, but these days he prefers to sort of do it in the evening in GMT. So for those of you around the world, this is a particularly useful thing to do. Also, it's been super useful for folks, including some of the peer supporters in the room, to go to his deep dives. Now, his deep dives, you can learn more about them on the Notion homepage. You can learn more about Vincent through his transformation of the week or through his Notion homepage. And you can find him on the calendar here at 9 a.m. PT on Tuesdays. And that'll be sort of a 90-minute session that he'll go into deep depth on stuff in more of a small group capacity from week to week. I'll tell you more about what he's going to cover at the end of this session. It'll be a little bit more useful to you than after you get some context. One of the things we always like to do, and I always like to tell you guys about, is we are listening to you. We hear you, and we're here for you. So thank you, everybody, for providing feedback. We got a ton of great yay feedback. Good start, great start, excited. Good vibes, great vibes, dope. Thank you for the shout out on Notion, GitHub, and Discord being good. Okay, that was the first one I've ever seen on that. It's been a lot of iterations to get down to this. We continue to try to refine it. So more specific, detailed feedback, always super useful, especially from as we develop our product perspective. Shout out to one of the folks who joined us for AIE 1 and now is here in AIE 5. Thank you for noticing the logistics as well. So we got a great sort of set of yay feedback, but of course we don't improve with yay feedback. So I want to dig into the suggestions you guys provided as well. I appreciate all the content and all the material that you are putting in getting us up to speed, but it is a bit overwhelming. It's going to be a bit painful at first. If you're feeling this way, you're not alone. Just know that. You will continue to feel this way. In fact, being at the LLM edge is sort of constantly feeling this way, but it does get easier if you do this for a couple of years, trust us. It would be great to have smaller breakout rooms for improved focus and better one-on-one guidance. This is exactly what we have one-on-one office hours for. So you're going to get a much better one-on-one sort of environment in the office hours. We also have literally one-on-one support available during every breakout room. Todd's available and Duke is available to help you out if you need specific one-on-one help with anything during any breakout room throughout the cohort. There's a lot of cross-linking, so not everybody loves this, between Notion, GitHub, and within GitHub, the links aren't always consistent or working. Thank you for noticing. We have done our best to fix this for the links that exist, and we will continue to work to make sure that these are on point for the links that are going to exist. Would be nice if the transition gave more than 5 seconds. The peer supporters are aware of this. They're going to give you a heads up. Maybe a quick check before kickoff on access. Yes, we could do better during onboarding to ensure access, and we will in cohort 6. Thank you for that. This was an interesting piece of feedback. If 2 concrete hands-on examples can be provided before breakout rooms, I'd love to hear more detail about this from whoever left this, so please feel free to shoot me a DM. I don't quite understand this feedback, and you know, adding more is obviously very difficult. Every minute counts. Couple questions in the feedback as well. What notebook are we submitting as part of Homework 1 submission? You'll be required to submit a link to your GitHub as well as screenshots of the completed vibe checks. So not a huge deal to submit a notebook here. Screenshots is what we're looking for. So if there's some confusing language in the submission form, our apologies, we'll go ahead and update that. Good starting session can include details on what to share on Loom. This has been asked before, and we created a Loom about what to Loom in the feed in the homework assignment form. So definitely check that out. Also, do we cover mathematical foundations? Well, no, we do not in this class cover mathematical foundations. In fact, it's very difficult to get down to the level of mathematical foundations. We've done our best to do this in some capacity. Some of you just took LLM engineering with us, so shout out to all of the folks who are coming back for more. And LLM Foundations is a free 5-day email course that will dig into some of this. Look out for more deeper mathematical foundation content from us on YouTube, spaced out over this year. It's quite hard to get down to the level of actual calculations because of how much and how many are always going on. The assignment part is super confusing. No link in Notion. There was no link in Notion when this feedback was provided, but you'll always be able to find the links in Notion, in GitHub, in Discord, and in your email after class. Okay. With that, let's get into what we're going to cover today. Today, we actually cover prompt engineering and RAG. We did a bit of precursor stuff in session 1. Hopefully it set the stage and we're ready to rock and roll. What we want to do is we want to kind of get an overview of prompt engineering. We want to get kind of an understanding of embedding models. We want to provide one-on-one support for folks that need Git help. And fundamentally, most importantly of all, we want to understand RAG. RAG. That's what we want. So again, if you need help on this, we're going to open up a special set of rooms for you. Just pay attention and look for that if you're already excited about getting some Git help one-on-one. So we're going to talk about a few things as we get started today. We're going to talk about prototyping, we're going to talk about prompting, and we're going to talk about the application stack that we're going to use that's sort of born out of the way we can sort of think about prototyping and prompting. We're also going to talk a little bit about embeddings. This is an important prerequisite concept. You can dig into more detail in the LLM Foundations course, the 5-day email course, and fundamentally, this all leads up to RAG. Some of you may know who P. Marca is. He's been gaining steam these days as the new administration is going to come in. He's been spending his time between Silicon Valley and Mar-a-Lago, I believe, quite a bit. And so he's Mark Andreessen of Andreessen Horowitz, A16Z, one of the biggest venture capital firms in the Valley. And he created sort of the first internet browser that kind of went super viral and has been kind of a big deal in the space ever since. He has a ton of blogs. We're going to look at them. We're going to be able to ask questions against them. We're going to treat it like it's our private data and have some fun with it. He's been called the philosopher king of Silicon Valley in recent months, so kind of a fun connection. that we are coming back into play here in 2025 now. P. Markham more relevant than ever. We're going to look at some of his older stuff, though. With that, let's remind ourselves what we talked about last time. And we're going to keep reminding ourselves about this as we continue to try to get more and more context. All right, so we're going to generally use 4 prototyping patterns: prompt engineering, RAG, fine-tuning, and agents. When we talk about prompt engineering, we're talking about putting stuff in context, into the context window. When we talk about RAG, we're talking about giving the LLM access to new knowledge. And the way that we do that is we actually go search and retrieve stuff to put in context, in the context window. Fine-tuning is about teaching the LLM how to act. With many examples, we could actually put all of these in context. Fine-tuning occurs once we actually move them into the model and take them out of the context window, as we'll see. And agents, an easy way to think about this now is it enhances search and really enhances the retrieval process of RAG by giving the LLM access to tools, to live data, to any API we might hit and get some data back. When we go from prompting to RAG, we're optimizing what we're putting in context. When we go from prompting to fine-tuning, we're optimizing how the LLM will behave or act. We're going to need to optimize both of these things to create truly human-level performance in our applications. Agentic reasoning can be applied at any point, even within the model now. And generally, we're going to start by prompting, adding one-shot, two-shot, few-shot. That's examples of what we want it to do. Then we're going to do maybe some vibe checking, maybe some more proper evaluation before we go to RAG. And then maybe we'll look at the chunk size. And really in 2025, I switch this up a bit. Then we're probably going to give it access to some tools. It is the year of agents after all. See if that enhances search and what we retrieve. Then we might do something like fine-tune embeddings. Then we might continue to try to enhance our retrieval pipeline, give it different types of retrievers, make it more advanced, make it more sophisticated, and continue with potentially fine-tuning the chat model itself. All right, let's talk about prompting. That's where the story begins. You know, it was June of 2018 when GPT came out. And GPT said, you know, actually, when we pair supervised learning with unsupervised pre-training, it's pretty dope. And they noticed that task-specific performance steadily increased as they did more and more unsupervised pre-training. So the more pre-training they did, focused on specific tasks like question answering, talk a lot about that today with RAG, but also like linguistic acceptability or sentiment analysis. You could get pretty far with just pre-training alone, but you know, you're not getting up to like 100% accuracy. And you can get pretty far with supervised fine-tuning alone, but not on every type of task, maybe more on sentiment analysis than anything else. But when you do this pre-training and then you do some fine-tuning, you just get this sweet result. You're just crushing it. And so this process, this two-step of unsupervised pre-training and supervised fine-tuning, they were like, yo, this works super well, super dope. But they were like, well, the generalization, it doesn't work super well. There's some bias that we're kind of worried about, and we don't have enough compute. Fast forward to February 2019, they were like, actually, if we just throw more compute at this, we don't even need supervised fine-tuning. We're getting surprising results without it. In fact, all we need to do is prompt the thing. And that was kind of worrisome for a little bit. A year and a little bit later, after they stopped worrying about it completely. GPT-3, well, I won't say completely, wasn't fully released at first, but it was released. And they were like, yeah, this scaling thing really works. And they were like, we're entering a new paradigm where these AI models, they don't need like the same thing that we thought they needed. They can be more like us, maybe. We don't require all of this super duper specific task data. We just give like straightforward instructions to one another. And even kids can do this. In fact, this is the #1 rule of prompt engineering: clear and specific instructions. The second most important rule of prompt engineering is to put the right stuff in context. One way to think about this is you want to tell the LLM how you want it to act, how you want it to present itself. Is it sad? Is it happy? Is it raining outside? You'll see this kind of thing in a lot of your under the hood analysis. You'll see this kind of thing in a lot of your evaluation of evaluation prompts. There's another piece of context here, and that is retrieved context, which we will most certainly come back to today. And when we think about input, we can think about what we're putting in. One shot, two shot, few shot. What are we putting in context? This is from the GPT-3 paper. Turns out that if we put no shots, that's an instruction only, we can do like meh. With one shot, with a big enough model, we can do pretty good. And with more shots, we can do more better. Dope. It turns out that this kind of behavior of kind of it's like going along, it's not crushing the benchmarks, and then all of a sudden, like you give it the right stuff, it starts crushing them. Whether you look at a benchmark like GLUE, the general language understanding evaluation benchmark, or super glue or extra duper super glue, you're kind of seeing the same thing that we saw in GPT. And you're seeing that we're seeing this crazy improvement. We don't even need fine tuning to do this anymore. We just need like examples in context. Now it's important to understand that this zero shot is instruction only. And we can think about instruction only as going on a spectrum. From instruction only, translate English to French, to giving it some examples. One example, that's one shot. A few examples, that's few shot. But if you give it 1,000 or 10,000 examples, then all of a sudden you're basically doing fine tuning. Now, one of the questions they asked at this point was, how can I get the LLM to follow instructions, not just with specific one shot, two shot, few shot, but in general? Entered what we came to know as like GPT 3.5 Turbo, Instruct GPT, which was better than GPT-3 at following instructions because it used fine tuning with instructions. This is called instruction tuning. This is more like what we're looking for. Follow the instruction. And this opened up the door to this idea of like, you know, just predicting the next token on the data from the internet is actually different than follow the user's instructions. Be helpful and be safe. Don't be misaligned with us. Now, fine tuning and alignment and all that stuff, all that's prerequisite to this course. We actually don't care a whole lot about that to build. This is from the Instruct GPT paper. Starting with a set of labeler written prompts and prompts submitted through the OpenAI API, they did a bunch of cool stuff, RLHF, et cetera. Hey, we're going to use the OpenAI API today. That's pretty cool. There's also chain of thought you can use in the input. This is telling this thing, think through it step by step. There's a paper put out by Google in 2022 that covers chain of thought. It's pretty dope. You should check it out. But you can actually shortcut this by looking at the event we did yesterday, where we covered chain of thought in quite a bit of depth because it is the core idea behind these large reasoning models. That aside, we want to know what the output is. We want to be specific with the output. hey, I want it like this. You got to tell it, you got to instruct it. All right, so GPT-3 was like dope, zero shot, few shot. It's pretty good. All we have to do is put stuff in context. We can go from zero shot to one shot to few shot to fine tuning. And this is exactly the dimension that we've talked about with prototyping. As we go from prompting to fine tuning, we're optimizing the behavior. And as we go from zero shot to fine tuning, we're actually going from prompting in context to kind of shoving it into the model, doing some rewiring. How do we build this stuff? Well, we build it with a particular stack. Let's call it like an AI engineering stack. The tools that support these skills. The tools that were put out by actually A16Z, Mark Andreessen's, this actually aged extremely well. You won't be surprised to see, this was from June 2023. It's held up quite well. You won't be surprised to see that the stack that we're going to use is based on, our good friend, the design pattern in context learning. And the design pattern of in context learning from an LLM stack perspective can be broken down into sort of three pieces: embedding, retrieval, and inference. We're doing the data, we got to get the prompt right, we got to put the right stuff in context, and then we got to actually do the prediction. This might be a little bit hard to read. You'll come to know this quite well. The first piece is the embedding piece, and this is where we get the context in. We do the data engineering, we do the data pipeline stuff, Mina, and then we actually are using this embedding model, this vector database, this orchestration. We'll do this today. When we talk about retrieval, you're also going to leverage some additional maybe outside APIs, access to tools, let's say, some agentic stuff. And you might mess with stuff in a user interface, right? A UI, a chatbot, and you might open that up to allow other people to use it as well. What's going on the back end? Well, that's where kind of the LLM ops can happen. And that's where, you're going to choose your model, you're going to host it, you're going to set up inference endpoints, you're going to do all that good stuff. Today, we're just going to use like the OpenAI API. Super simple, super straightforward. We're going to build something really simple today, actually. We're going to use Python to build RAG from scratch. One last thing I want to tell you about, which is when we hit the API, we're going to hit it in a specific way. We're not going to hit it like other people hit chatbots. Many of you are familiar with APIs, some of you not so much. The input isn't text and the output isn't text. We're actually inputting a list of chat messages and we're outputting a single chat message. These chat messages have roles: system, user, and assistant. This is important and it's not going away. The system level role is like kind of the zero shot level role. It's kind of like the meta instruction. You are a helpful assistant. Oh, look at that. You are a helpful assistant. The user, that's kind of you. That's your user. That's, if you're looking at people hitting this, it's whoever's using it. And then the assistant is the AI responding. Or it's you providing an answer, like to a one-shot, two-shot, few-shot example. We'll see plenty of this throughout the cohort. But I want to take an aside, because in order to get started with all of this, we got to get set up. And some of you were totally legit getting set up. You do this every day. You use Git, you log in the morning, and you're pushing stuff. Some of you not so much. Some of you almost never use Git. Some of you maybe have never used Git until we kind of forced you into this challenge. Now, to do the challenge, cheating was okay. You could fork the repo, you could duplicate our space, you get away with the challenge. But today is sort of not okay to do that. Actually, the correct way to have done the challenge looks more like this. Now, if this is unsettling to you. You probably feel like the student we heard from earlier. But it's okay. We're here to support you. We're going to tee up what we're going to do today in the breakout room. We're going to tee up homework 2. And we're going to show you the correct way to do it. That's what Wiz is about to show you right now. How to actually get this set up to start working on it. Now, if you watch this and you're like, oh my God, I can't do that. I want you to go to the one-on-one support room that we will have open while he's presenting. It will be open for the next 25 minutes. If you watch Wiz and you're like, yeah, I got it, okay. Great, just hang out. You'll miss one thing if you go to the room. You'll miss our discussion of embeddings, which is a prerequisite anyways. So especially if you took LLM E3 and you're confused on Git, you should go to the room. But if you want to stick around and you don't understand Git, then I will ask you that you please do not interrupt your breakout room later with Git issues. Your peer supporter will ship you out of there and we'll get you to one-on-one support. So you can go now or you can go later. It's up to you. But Wiz is going to show you how to get set up. Wiz, over to you.
All righty. So basically what we're going to do is go through everything from scratch, from zero. So what I'm going to do is I'm just going to open up fresh cursor and then share my screen. So we're going to go through this together in a way that that hopefully makes sense. So I'm going to share my screen. We'll go ahead and share the cursor window, which should be, whoop. You should be seeing the cursor window now. And the idea is pretty straightforward. So cursor, if you're used to, ignore the cursor terminal there for a second. If you're used to, your VS Code, this is basically the same thing. So it basically is a stretch. It's literally the same thing. It is a fork, in fact, of VS Code. So all I'm doing is opening up my AIE5 repository, which is going to contain, everything that we've done so far. What I'll do is when we're in this repository, I'll go ahead and I'll open a terminal, and then I'm going to zoom in a lot so we can see the terminal a little bit better. Here we go, and I'll drag it out here so we got a little bit more room like this. Okay. So basically, the way that this works is we're going to be able to see that we're in a repository. Currently, we're ready to rock. But what I'm going to do is I'm going to do a git pull upstream main. This is going to pull in my desired repository, which is already done. Okay. Now that we've git pulled origin main, we can see that we have this embeddings and rag assignment, right? So this is the embedding and rag assignment. We're going to see some stuff in here. This is going to contain a bunch of different folders. We're not going to worry about all of those folders too much, but we're also going to have this idea of a pyproject.toml. So this pyproject.toml here is going to be our list of dependencies. And this is how we're going to interact with the Jupyter notebook that we want to use. So I'm going to go back to my original terminal here, and I'm going to make sure that UV is installed. We need to make sure that we have UV. This is outlined in the instructions. So in the README, we have, the first things that we're going to do is install UV, and then we're going to use UV sync. We're going to use UV sync in order to make sure that we have our dependencies installed. So I'm going to go ahead and I'm going to get those from the dependencies that are available in the assignment. So I'm going to hit UV sync. You're going to see that stuff happens. You'll also notice that happens very quickly, which is a little bit different to, if you're used to something like Conda, UV written in Rust, by the way. It is very, very quick, very snappy. Okay. Yes, it's Uma, exactly correct. definitely switch to cursor if you can. The switch is totally seamless. It installs all of your extensions that you have from VS Code as long as you accept that. There's a way to follow uh, the session page to make sure that you get cursor set up correctly. So we built a resource to make sure that your cursor is set up the way that it should be. Now that we have this UV environment installed and we have our UV lock and it's all ready to go, we're now going to start thinking about how we want to do like a notebook, right? So we have the ability to select kernels in our notebook. We have a lot of different kernels in our notebook that we have the ability to select, and we just want to make sure we're selecting the one that makes the most sense. The way to be the most sure about this is to open folder, and then in your AIE5 repo, just open the folder you're working on, right? So this is going to only be the thing we're working on. We are going to go ahead and not worry about this pop-up. And the whole idea here is that we want to be able to make sure that our interpreter, which is our Python interpreter, is set up so that we have the ability to interact with our IPy kernel, which is this. All this means is this top thing here. Once we've got this kernel selected, which we can do by hitting the big one with a star that says recommended, we are good to start moving through our notebook, which we can do by just navigating down and clicking cells and hitting play and seeing things happen. This is the way we're going to do every assignment that happens in VS Code. So we don't worry about this step if we're in, say, a Jupyter notebook or whatever, but we do care about this step if we're in just VS Code, which is going to happen, relatively often in this particular course. So what we're going to do is, now that we have everything up and running and working and being happy, we're going to go ahead and we're going to work through this embedding notebook. There's a lot of text that you can read that helps to understand embeddings. We're going to focus mostly on actually running some code today. The idea is we want to be able to do one very specific thing with our embeddings, right? The embeddings is like the way that we can have the machine determine what is or isn't related to each other, right? So for humans, it's easy. If I tell you the sentence like the cat is happy and the cat is joyful, you're like, it does mean kind of basically the same thing, right? Or if I tell you like, hey, that box is orange versus like, hey, that box is the same color as a pylon, right? Like you're going to be like, okay, I mean, the box is orange. I get it. The machine, right? The algorithms that we're using, the computers are terrible at this out of the box. There's a lot of different interesting ways that we can think about doing this, right? And throughout history, we've had loads of fun ways to do this, but we're going to focus on kind of like the most ubiquitous pattern, which is using an embedding model, right? So when we say the word embeddings, what we mean is some numeric representation. It's a vector, in fact, that points to somewhere in some very high dimensional space, right? So you can imagine like a word cloud in 3 dimensions where the closeness of 2 words is going to be related to their the closeness in meaning, right? So if I have a big word cloud and I imagine something like, we can look at this 2D example here, right? But if we imagine like adult might have words next to it, like grown up, this kind of thing, baby, infant, this kind of thing. That's the idea of embeddings. Just a way for our the algorithm to be able to get this. Okay, now all that's great, but how do we actually use them, right? How do we determine they're close? Well, if you remember kind of, math, or if you're coming from a machine learning background, right, we're going to use this thing called cosine similarity. What this is going to do is it's going to tell us, yes, a vector is both magnitude and direction. Andrew, very good. But yes, the cosine similarity is going to tell us is the vector pointing in the same direction? Because while it's easiest to understand embeddings in this kind of way, right, where we have this 2D plot, they're actually much more high dimensional. It gets a little hairy up there in the highest dimensions. But the idea is pretty straightforwardly that we have some ability to determine if they're pointing in the same direction or not. And what we're going to assume is if they're pointing in the same direction, then they are very related, right? The math works out. That's true. If they are not pointing in the same direction, then they're less related. And there's a gradient, right? From very related when they're pointing in the same direction exactly, and then oppositely related when they're pointing in opposite directions. So what we're going to do first is just define this function, which is just this equation that we've got through NumPy. Very cool. And then we're going to need to provide our OpenAI key, which we'll do in order to hit the endpoint that we need. So we'll do that here. This is going to let us use the embedding model from OpenAI. Very fun. And yes, okay. That's the idea. And so that's where we'll, I believe, pause for a moment because we'll hear a little bit more about how to get the embedding models from Greg, and then we'll come back and we'll see how we implement them in the code.
All right. So if you're struggling with Git ideas, dev environment setup, please do go ahead and seek some one-on-one support now. For the rest of you guys that are like, nah, that's all good, just hang out. We want to talk about embeddings with you. Now, this is a really often misunderstood concept because this word is so difficult. What does embed even mean? What does embedding even mean? It's quite challenging. And you can look these up and you can find the definitions. And, when you look up embedding, you see the mapping of one set onto another. And the way we can easily think about it is the mapping of language into vector space. But really, you're going to hear a lot of different types of embeddings as you study LLMs and AI. You're going to hear like embeddings. Now, when somebody says this, it could mean either embedding layer, like you'll find within a transformer, or embedding model, like the one Wiz is going to show us we can just use from OpenAI. And it's going to depend on the context. But either way, we're going to be dealing with embedding representations. And the embedding representations are just basically turning our words into mathable representations. We need to be able to do computation. And it's very, very hard to do that on words. We need some math. We need some vectors. And so when we talk about embedding layers, that's the trainable layer in the transformer generally is when we're talking about LLMs that maps the input tokens to the dense vector embedding representations. If you read the Attention is All You Need paper, you'll see that there's actually different types of embeddings. You can have sort of like out-of-the-box embeddings, or you could have learned embeddings. And actually the transformer, as we know, it uses learned embeddings. And then there's the embedding model, which is a language model, typically like a BERT style, bidirectional encoder representations for transformers. This is something that is, again, prerequisite knowledge that generates embedding representations so that the input and output have a similar meaning. And then, there's also this other idea of using these embedding models for RAG. We want to embed representations of our data. We want to take our source docs, we want to chunk them up, we want to run them through an embedding model so that we can put those vectors into a vector store, a vector DB. And so embeddings, they're just like representing words in vector space. So this is a fun quiz that I've shown quite a lot. Where do we put the word cow, right? Well, we put the word cow at C because puppy is to dog as calf is to cow. And so we have sort of two dimensions here. We've got the dimension of maybe age. We've got the dimension of maybe size. But, it's like, well, how many dimensions do we need to represent words and sentence level stuff in general? We need thousands of them. And that's what you'll see in common embedding models today. These embedding models for the last 10 years have been shown to be successful on many downstream tasks so that we can, again, do this math with these representations. The famous example from 2013 is called word2vec. Iconic. King minus man plus woman equals queen. People were losing their minds that this worked. It was dope. And, you know, today, as we'll see, like OpenAI has embedding models. You can get embedding models off Hugging Face. You can get embedding models all over the place. Everybody has them. And I guess I do want to show this video. And we'll see if the volume's okay here. Whoop. Can I get a thumbs up, Mike C, on the volume?
Consider the phrases American true mole, 1 mole of carbon dioxide, and take a biopsy of the mole. You and I know that the word mole has different meanings in each one of these, based on the context. But after the first step of a transformer, the one that breaks up the text and associates each token with a vector, the vector that's associated with mole would be the same in all 3 of these cases, because this initial token embedding is effectively a lookup table with no reference to the context. It's only in the next step of the transformer that the surrounding embeddings have the chance to pass information into this one. The picture you might have in mind is that there are multiple distinct directions in this embedding space, encoding the multiple distinct meanings of the word mole, and that a well-trained attention block calculates what you need to add to the generic embedding to move it to one of these more specific directions as a function of the context.
All right, so this embedding representation idea, again, we go back to this words into numbers piece. It's useful because we can do math, but what is the math for? Well, you know, think about the way we're training these models. What we're going to do is we're going to say, you know, we want this kind of thing when we're at the sentence level. A person on a horse is kind of close to a person on a horse. You know, the input words and the output numbers, we want them to sort of mean the same thing. We want them semantically to sort of mean the same thing. And meaning the same thing, what that means is it means that they're sort of close together in embedding space. Now, here's where we connect it back to everything we've talked about already today. There's 2 types of embedding models. One of them has context. Context, since 2013, and even before in NLP, has meant tracking the position of words. Makes sense. No context, that's like the bag of words stuff. If you guys remember the classic NLP, my data scientists out there, the TF IDF was like super legit, right? But still no context. Now, it turned out that there's lots of ways to get context. Word2vec looked at a couple of those ways. Also, a neural network, you can get context. You can look at how things are relative to one another. Intuitive, really, if you think about deep learning. And what is a transformer? What is a GPT model other than a big old neural network? Right? It matters. The context, it matters. Whether we're looking at a big old massive LLM or we're looking at word2vec. And so like this idea of similarity, it's kind of very fundamental. When we encode our language into embedding space, we then have to decode it back into language space. And so we'll see that embeddings and also RAG and also like recommendation algorithms and kind of a lot of the stuff we're doing with search is kind of just similarity all the way down. So back to you, Wiz, to finish up the primer here.
Yeah, so let's clarify a few things that that we heard about, just so we're making sure we're all on the same page. So it's really useful to think about these things as being quote unquote close together, but we don't really care about their closeness. We care about the directions that they're pointing. This is the fundamental, mental leap you've got to make for cosine similarity, for instance, to make sense. Once we have that understanding, there was a couple great questions as well in the chat. Like, what's the difference between a vector database and a vector or an embedding model? So our embedding model is going to be what generates the actual embedding vectors, and then we're going to think about storing them, a little bit later. But the idea is once we have our embedding model set up, which is just pointing at OpenAI, we can feed in sentences, and then we can get back vectors, right? So you can see that we have a natural language sequence here. I love puppies, I love dogs. And then we can get embeddings for each of those to get a puppy and a dog vector. Now, someone asked a great question, right? What is the, how does it work that it's all one vector, but it's an entire sentence, right? And the idea is we use what's called mean pooling or max pooling, but the math really just works out such that if we take an average of every position in the vector, right, with every word in our sequence, that the meaning of the resultant averaged vector, or using a different method, max pooling, which we'll not worry about too much for right now, these vectors actually represent the meaning for the entire sentence, right? So basically each vector's contribution is included, and so we wind up with one vector that represents the entirety of the sequence. So that's why we have the sentence "I love puppies," but we get one single vector out, and we can use cosine similarity to determine that these vectors are pointing in a very similar direction, right? The maximum here is going to be a value of 1, and the minimum is going to be a value of -1. 1 means extremely close, and -1 means exactly opposite. So this is the idea of using this. And then you can see here, if we use I love puppies and I dislike cats, these vectors are not as related, which we would hope, right? The next thing we can do is math. So we can just, like Greg showed, right, in the slide, we can just add and subtract these. So we can take king, minus man plus woman, and we can separately get the embedding vector for queen, and we can see that king minus man plus woman is very close to queen, which makes a ton of sense. So the math behind these and the concepts behind them are maybe quite dense, but the basic idea is we have two vectors. We can measure if they're pointing in the same direction, and if they are, they mean the same thing. And that's as you'll see in the next code demonstration, as Greg talks to us about how we can apply things like this, an extremely powerful notion. So with that, I'll pass you guys back to Greg, and we'll get rocking.
All right, thanks, Wiz. So with that, we're going to go ahead, and it's 7:50. We're going to take our break a little bit earlier today. Those rooms are still open if you would like to spend the next 5 minutes or so talking about dev environment stuff to one-on-one folks and peer supporters. But go ahead and take a quick 5, and when we come back, we're all going to come back, and we're going to map what we've learned already into RAG. Stick around, ask questions if you want to hang out and chill with us. All right, break it out, shake it out. It is time, now that we're back from break, to RAG. All right, let's do RAG. Let's go to RAG. Here we go. So what's the point of RAG? Well, the point is, as we continue to see in papers even today, people really don't like hallucinations. This is number one complaint from enterprise. These things are lying to me. I can't put them in front of my customers. Big, big problem. What do we do with humans? Well, we are like, yo, are you lying to me? Where are the facts? Where are your references? Where did you get that information? We're doing the same thing with LLMs. Where are the facts? Where did you get that? Where's your information? RAG is Retrieval Augmented Generation. We retrieve reference material. We augment what we put in context into the prompt with that reference material, and we generate better, more fact-checkable answers. Now, with embeddings in mind, what we want to do is we want to map our data and the questions we're going to ask so that they're kind of both in embedding space. So we can say, the question we want to answer, do we have anything in our data that could be relevant reference material to retrieve? We want to search our data for stuff that's similar to the questions we want to ask. Similar here means the same semantic meaning. That means it's going to provide relevant context for us. Man, context is just one of those words, isn't it? Now, we like to break down RAG into two pieces: dense vector retrieval and, oh, look at that, our good friend, in-context learning. We ask a question, we send that question or query to the embedding model, we convert the language representation into an embedding space vector representation, and then we go and we look for stuff that's similar to that in our data, in our vector store, in our database. We set up a prompt template in context, and it says use the provided context to answer the user's query. You may not answer the user's query unless there is a specific context in the following text. If you don't know the answer, say I don't know. Just don't hallucinate and don't lie to me. We return the reference material. It is no longer in embedding space. Now, this is interesting because when we get into fancy techniques, we sometimes sort of use this point that we go now, after we've found the similar stuff, we go back into language space to bring the references in, and then we shove that into the LLM, which is going to send it back to embedding space in order to generate the output. So we have this dense vector retrieval process. We have our in-context learning. This is almost all of RAG. And then we put it all into the chat model. Then we get our better answer. And, you know, when we talk about putting the R in RAG, we already kind of talked about the dense vector representations, the embedding representations. We can kind of connect that now to the stack, right? Like here, this is our embedding model. Do we need to know exactly how it works? Well, insofar as we know that we can kind of use it along with the vector database to get similar stuff out, that's probably enough, because these things are just APIs now. Now, we can do fine tuning, and we will, of some of these, but we can kind of just pull this off the shelf. And then we have an embedding model. We can create embedding representations, whether it's with our data or our queries. When we put the R in RAG, really, we're talking about retrieval. And the retrieval process is kind of simple. We ask the question, we search the database for stuff that's similar, we return the stuff. Similar, again, means vectors. It means embedding representations. It means math. It means dot product. It means cosine similarity. And we're returning it in natural language. Remember, we talked about embeddings for RAG. We want to embed our representations of our data. We need to chunk them up. And then we need to run all of those beautiful chunks through the embedding model, put it in a database. That's our database right here. What we do is then we wrap what's called a retriever around the database, and guess what it does? It retrieves. And, you know, like, there's additional discussions that we'll have as we continue this course, like, well, which vector database and which embedding model should I choose and why? I wouldn't worry about any of that right now, because we're actually going to use an off-the-shelf embedding model, and we're going to just build our own vector database. So we don't even need to worry about people's vector databases. And the second piece of this is, of course, in-context learning. That was such a great question in the chat here. Are prompting and in-context learning basically the same thing? Was essentially that, what's the difference between prompting and RAG? Well, both of them are leveraging this idea, this sort of meta idea of in-context learning. Prompt engineering is literally such a meta idea. It's so important. Like coding of the future will mostly, well, at least in large part, be done with natural language. Scripting is a step towards that, and these LLMs are just taking it to the next level. So prompting is kind of fundamental. Prompt engineering really is kind of what you need to do when you're building these applications. So we're actually putting stuff into the prompt. We're putting new knowledge in context. And remember, we're doing all of this without any need for any fine tuning, simply by prompting, simply by putting the stuff in context, simply by putting the prompt template in place. And you know, if we do retrieval well, generation is done better. RAG says that this occurs via prompt augmentation. And really, as we'll see, when we augment the prompt with even more information, we search more data from the internet, from APIs, we can get even better. And we'll see that when we cover agents. So we have dense vector retrieval, we have in-context learning. That's almost RAG until we pump it into the chat model, we get our better answer. That's RAG. We're going to do some RAG with some blogs. We're going to use some off-the-shelf OpenAI models. Specifically, we need an embedding model and a chat model. Both of these are LLMs, but when people say LLM, they're kind of assuming you're talking about a chat model. That's one that's been instruction tuned to follow instructions. It's one that's been tuned to be good at chatting. And so the data is just an old set of blogs. Not that much, like 200 pages. And we'll create our own vector store. It'll be a custom job here. And we'll just load the data in. We'll chunk it up. We'll embed the data. We'll store it. Remember, and this is really important, what gets chunked gets retrieved. You know, like I really like this idea that there's like a perfect chunk. The golden chunk is like exactly what I need to answer my question. Well, how should I chunk my data so I can get it? Well, what questions are you asking? And on we go as we develop our LLM applications. Now, chunking is an art of its own. It's just breaking text up into smaller pieces. Like, how small should they be? Should they be words? Maybe sentences are better. What about paragraphs? When we put an Alice in Wonderland book in and we do sort of a default best practice chunk, this is kind of the size of a chunk. You can do really dumb, easy chunking strategies, like fixed size, where you have a number of characters you want to take, and then an overlap, but you'll cut it off. You'll cut it off right in the middle of words, and that's clearly not good for context. But there's other text splitting, and this is kind of the best practice, which is called recursive text splitting, and it kind of looks for where are the characters, keep them together. Where are the spaces? Maybe that's better to cut at a space. Where are the new lines? It's even better to cut it at a new line. Where are the double new lines? And so what we're going to do is we're going to build with this stack today. We're going to build our own Python vector DB. We're going to use OpenAI models. We're going to use the OpenAI Python SDK. And we're going to do Pythonic RAG. Wiz, over to you.
Oh yeah, snake rag. Okay, so this is the most we'll do a custom solution because we will quickly learn that there are powerful frameworks that exist that can help us do this much quicker. But we will do this in Python, just to say we did, and start from kind of zero. The first thing we're going to do is get our notebook open. We're going to click on venv. We're going to select another kernel, Python environments, and again, big star venv, give her a click. Now we're in our virtual environment, powered by UV. Thanks, UV. If you are on the NVIDIA driver 552.44, you will need to roll back your driver. or sorry, if you're ahead of 555244, you'll need to roll back to 55244. This might have been fixed for you, but if it isn't, there you go. Okay. So this is the system we're going to build, and it looks like a lot of stuff is going on, but it's not too bad, right? It just looks like a lot of things are happening. The big stuff, though, is we have our our input, which is just going to be some text. We pass that text to our embedding model, which is going to return a vector. We're going to associate that text and that vector using our just some Python. And then we're going to store it in a vector database, aka a dictionary, and then we are going to leave it there. When we make a query to our model or our system, we are going to do the same thing we did for our input, which is we're going to get an embedding vector, and then we're going to use cosine similarity in order to determine which are its quote-unquote nearest neighbors, and then we're going to use that to augment our prompt with a bunch of context. And then we're going to feed all of that prompt and that context, plus the user's query, into our chat model, which is going to go ahead and return to us our output. So a lot of stuff going on, but it's simpler than it looks. We're going to import some stuff from the AI Makerspace, little RAG library that we built for this. We're going to use this nest async IO. This is just to avoid any weird async issues. So this is the first bit that we're going to do. We're going to take some raw source documents. These are the blogs Greg was mentioning. And then we're going to go ahead and we're going to push this to our embedding model after doing some chunking. A lot of questions about chunking. We're going to spend a lot of time thinking about chunking in our time together. But the idea is we could just have one document and get an embedding vector for just that document. But you can imagine that chunks give us the ability to understand specific parts of our document, or in fact chunks, right? And this is useful because this averaging process is gonna lose some specific information, right? We might have a section of the blog that's about topic A, but there's 90% of the blog is about topic B, and we might lose a little bit of closeness to that document. As well, this is less so a problem than it was maybe 6 months ago, but LLMs still struggle with really long contexts in order to produce great factual responses. So we want to feed basically just exactly the information the LLM needs and no more than that. So choosing how big these chunks are, choosing how we should chunk, this is a very difficult thing to do. It's also an art, not a science yet, but we are going to chunk. Today we're going to chunk extremely naively, which will be nice and easy to implement in code. We are also going to load some text. Our text loader, our text file loader, you can see is just wrapping with open. Then we have the first 100 characters of our document, which is the pmarkup blog archives, yada yada. It's a big piece of text. So what we're going to do is we're going to just split her up. This is going to be done based only on character length. So we're going to split, a sequence of characters, which is what we're effectively loading into memory, and we're going to split each of those into its own chunk, and that's it. We're not thinking about sentence structure. We're not thinking about document structure. We're just saying, hey, if you exceed n characters, stop. That's a chunk. And then we're going to carry on for the next chunk from the n+1th character. Okay. So we're going to do this, and that's going to give us these chunks, which is just, long strings of text. So now we do our embedding process. Once again, we're going to give our OpenAI key, and then we're going to use this extremely fancy vector database, which is going to be a default dict with NP array. So we're using NumPy to store our vectors because it's just a little bit faster when we eventually do that cosine similarity. And so we just have a dictionary that's going to be filled with these NumPy arrays. That's it. That is our vector store. This is our vector database. Vector databases that you find in the wild are usually going to be slightly more intelligent than this, right? They're going to have some kinds of technology and processes which makes searching faster to allow us to search, as we head into the trillions of vectors. This is going to become slow very quickly. As we'll see in a second, we probably can understand why it's going to be slow. But the idea is that this is like most naive implementation of a vector a database. However, people advocate for this solution even to this day if you have a very small set of vectors. Okay, there's a great question from chat, right? What does it mean by a vector with dimension 1536? So if you remember Greg's example where we had these two axes and we had some dots and it was like, where does C go or whatever, right? Well, that's a two-dimensional embedding space. Our embedding space is quite a bit bigger at 1,536 dimensions. You can loosely think about each of those dimensions as an axis on which we are going to think about where the vector is stored. So like, how young or old is this thing? How green is this thing? This kind of information. Okay, we have a question that you guys have to answer here. Is there any way to modify our dimension? And what technique does OpenAI use to achieve this modification if there are? Very cool. Then we're going to use some async because async is better than not async marginally. This is going to help us get many responses from our embedding model quickly. We're going to then build this build from list function, which is going to take a list of strings and it's going to convert them into vectors. And it's going to insert them associated with the text that generated the vector into our vector database. So we can instantiate our vector database here, and then we can use asyncio.run, which is going to run a new loop, which is why we have to use nest asyncio, and we're going to go ahead and build from list using the chunks from the pmarkup blogs as our input. And then we're going to basically, the question is why async, right? Why is async useful? And you can discuss with your group or answer from previous knowledge. So all we've done so far is got our source document, split them into chunks, send them over to text embedding 3 small, which is OpenAI's embedding model, and then we store them in the vector database. That's it. That's all we've done. So the next thing we need to do is enable some ability to search this structure that we've created, right? We have this vector database. We're very excited about it. It has all of our text and it has all of our vectors, but now we need a way to search through it, right? We have a new vector. We want to see, well, what's the closest thing in our vector database to this vector, right? In terms of meaning. Well, what we're going to do is we're going to build the ability to search by text. What this is going to do is it's going to take our text, it's going to convert it into a vector. Now, this is a very important step. It must be converted into a vector that is exactly the same embedding model that was used to create the vectors in our vector database already, right? And you can imagine that the reason is because if I have 3 different embedding models, they're going to put, the word cat in 3 different places. So if I use a different vector or a different embedding model, it's not useful, right? They don't map to each other at all. So what we have to do is make sure we're using the same embedding model that we use to build our vector database as we use to query our vector database. And then we're going to do a very slow thing, which is going to be just looping. We're going to loop through every vector and we're going to see how close it is. And then we're going to return a list that's sorted by closeness, right? So highest cosine similarity score to lowest cosine similarity score. You can imagine that this is extremely slow very quickly, right? Even if we have tens of thousands of vectors in our vector database, this is already going to be unmanageably slow. And so we have to have technology that helps us make this faster. And that's why we oftentimes are going to use vector databases that have these things built in for their search process. Things like approximate nearest neighbors, things like clustering, all kinds of different very fun things that we'll talk about as we progress. We're also going to see this K value. This is going to be our top K. Top K is, you're going to hear a lot, and basically just means, the top K closest documents. So if k was 1, it would only return the vector which matched with our query vector with the highest similarity score, versus if we have 3, it will give us the three vectors sorted by their closeness, their top 3. So this is the idea. Then we have our prompts. So this is the zero-shot in-context learning that Greg was telling us about. We're going to just give it a task, and it's going to do the task. That's what this means. We do have this concept, though, of different roles. We're not going too deep into this, so come out to an office hours if you want to learn more. But the idea is that we have an extremely straightforward way to interact with our LLM, which is going to be by giving it a role that we're trying to interact with. The system role is going to be things like instructions, telling it how to behave. The user role is going to be the actual query that we care about, and the assistant role is going to be its responses. Now, you might ask yourself, well, why the heck would we ever want to use the assistant role? Well, if we want to provide some few-shot examples, for instance, it's extremely effective to give the LLM this sequence and make it think like it produced that output, right? This is a way for the LLM to be able to understand how it should be producing outputs. So that's why we'd use that assistant sometimes. For the most part, though, we're going to stick to system and user. Systems where we're going to describe what we wish to happen, and then users where we're going to ask for that thing to happen. We're going to go ahead and just wrap some strings. We're going to use this fancy regex to, parse out basically curly brace wrapped variables because we can, and that's it. We're going to be able to set the role, and there we go. So now we have our chat OpenAI. If you look through the materials in the GitHub repo, you can work through the prompting exercise, which is going to go a little bit more in depth on what's happening here. But basically, the idea is exactly like Greg said. We have a list of messages. We send this endpoint a list of messages, and we get a response, which is based on that list of messages. Easy peasy, lemon squeezy. We have a question here. Are there any ways we can achieve more reproducible outputs? We have to include the qualifier more here because we cannot get to totally reproducible outputs through the OpenAI API. We can get to mostly the same every time unless they change anything, in which case it's no longer the same. So there you go. Then what we're going to do is we're going to essentially create a way to prompt this. So we're going to set up our chat OpenAI instance. We're going to have this prompt template, which is going to contain a content variable. We're going to use this prompt template to create the prompt. We're going to do the same thing for our system prompt, which is provide this template, which has an expertise variable. And then we're going to create the prompt from the template. And then we can send the messages, which is going to be creating the message from this particular variable. So you see here that the system prompt template says you're an expert in expertise. You always answer in a kind way. So when we use create message, it's going to create a string that says you're an expert in Python in this case, since that's what we put expertise as. Then, of course, we're going to have our user prompt, which is going to create message. This is just the whole string is content. So the whole string will be what is the best way to write a loop. And then we can run this and get the response, and it's going to tell us how to write loops. Very good. So how do we extend this to RAG? All we have to do is make the prompt templates a little bit bigger and add some automatic context fetching. So what we're going to do is we're going to say, okay, this is the RAG prompt template. Use the provided context to answer the user's query. You may not answer the user's query unless there is a specific context in the following text. If you do not know the answer or cannot answer, please respond with, I don't know. Then we're going to wrap that in our system role prompt. We're going to create our user prompt, which is going to contain context and user query. And then we can build our pipeline, right? Our pipeline is going to say, hey, whenever we get a user query, search the vector database for things that are most related to this user query and give me the top 4 most related chunks from our vector database. We're going to build those into a new line separated string, which is just going to be a big block we can shove into the prompt in the context window. And then we're going to do exactly that, which is create our system prompt. And then we're going to create our user prompt. We're going to fill in the user query with the user provided user query. And we're going to create our fill in the context with our context prompt, which was obtained through fetching things from our vector database. After that, all we have to do is return the response that we get. That's it. We're also going to, you'll notice, return a list of context. This is a good habit to be in, right? We want to make sure that we're returning context that is relevant and allowing users to see what we used to arrive at the response that we've arrived at. Okay, we have the next question, which is fairly straightforward. How could you make this better, right? Could you use prompting to make this better? Spoiler alert, the answer is yes. And then we're going to go ahead and create our retrieval augmented QA pipeline, which we can run on things like, what is the Michael Eisner Memorial Week executive problem? I have no idea what this is, but P. Marker wrote about it, and so we get the response. It refers to a situation where yada, yada, yada. And the idea is that it gives us the response. It tells us, based on these pieces of context, right, these 4 pieces of context from P. Marker's essays, it gives us exactly what we need to see. And then we have our final activity, which is change the RAG app in some way. Make it different, make it better, add something in Cursor, right? This is going to be a lot easier than it would be without Cursor. So we can do things like, if you were want to do this and not just get into the weeds yourself, we can do things like, add the ability to parse, PDFs instead of just text, right? I'm adjusting to a new keyboard. Please excuse my terrible typing. So here we go. And then we can control enter. And what it's going to do is it's going to look through everything that it sees in this workspace. It's going to think about it. And it's going to say, hey, wait, we need to extend text file loader class. So we're going to go ahead and do that. Right. So this is why we're suggesting Cursor for this class, because it can do things like this. If you want to do it the old-fashioned way and think about it and write code, please do. It'll be a great time to learn. But if you're looking for why Cursor is a good tool, you can imagine that this is an example of exactly that. Okay, with that, and I know it's a whirlwind. We're cruising through this. We're gonna spend a long time, the rest of our time together, in fact, getting into each of these points, getting deeper on each of these things. But for now, this is our introduction to Pythonic RAG. I'll pass you guys back to Greg.
Is that all there is to it, Wiz? I mean,
for now, yeah.
Yeah. So easy. Oh my gosh. All right. Well, it's time to hang out with each other a bit. And what we're going to do is we're going to open up breakout rooms, get back in your journey groups, get back with your peer supporters, and work on this RAG notebook. Okay, we're going to stay focused on the RAG notebook today. We really want to understand RAG. Again, if you're having trouble with embeddings, we have additional resources. You should check those out later. Additionally, if you're having trouble with Git and you really want to get it figured out, that's how you perceive getting value out of this class. We're still available with one-on-one support for you, 100%. So go ahead and head to one-on-one support after you get in your breakout room. They'll help you out. Todd will be there, and Duke will be there as well. Now, you'll also kind of probably be wondering, like, how exactly do I do this homework? The last one was kind of just screenshots. Well, your peer supporters will walk you through this. We're going to get comfortable working through code notebooks today. This is exactly how we're going to kind of rock it out in the coming weeks and months together. So just follow the directions in the README, chat about the questions that pop up. Feel free to take tangents and rabbit holes as your room is interested and finds it meaningful and worthwhile. And we'll see you guys back in 25 minutes to answer a few questions and wrap up RAG. Enjoy. We'll see you guys soon. We're back from breakout rooms. We've covered a lot today, and we have a few minutes. If you have burning questions, feel free to throw them in the chat, and we will get to them. One of the things I wanted to show you guys for a little chunk of fun is this is a really fun tool called ChunkViz. Throw it in the slides. You can play with it later. It is potentially useful if you have like small amounts of data that you want to play around with and you want to really try to dial this in. And you want to think about chunk size, you want to think about chunk overlap and Again, this is really an art and there's a lot to it that goes into it. As we build more and more, 17 builds in this cohort, we'll learn more and more ways to think about how to really optimize retrieval. So, today we really focused on RAG. We focused on learning about dense vector retrieval, using embeddings, using similarity search, and we learned about in-context learning. What we put in context is really important. When we track the context of words, that's kind of what a transformer is doing fundamentally. It's kind of what embedding models. Remember, pre-trained embedding models? That's what we used to call them. Back in the day, they were so cool. Now we talk about pre-trained off-the-shelf LLMs. And some of those LLMs are also embedding models. We learned that we needed embedding models and chat models to be able to do RAG. And, we also hopefully got set up today with Cursor and with our dev environment. You have all weekend to get set up. We're here for you. Check out the schedule for more on where to find people, when to find them. If you see someone in the lounge, feel free to jump in and say hi. Especially if it's a peer supporter, feel free to ask for some help if you need it or you want to discuss anything, jump on in. For today, though, I'd ask that you please provide us a little feedback. I think we'll have 3 extra minutes. And if you have questions, we'll go ahead and bang them out in the chat or let you ask them. But let's put 2 minutes on the clock and let us know what you thought of today, session 2 on embeddings and RAG. It's getting dropped in the chat right now. A quick reminder that next week we will have our deep dives starting. So Vincent is going to be covering deep dives. Make sure you join him if you're available and you have availability and interest. You can learn more. He's going to be covering the importance of prompting. He's going to talk about how LLMs actually predict tokens. If you want to dig into that, he's actually going to show you how to prompt different LLMs, system, user, and assistant. And he's also going to dig into some basics of LangChain and how to use basically the system, user, assistant setup in LangChain. I'd like to go to the first question that we wanted to go ahead and address. I forget who I saw start. Thurundu.
Yeah, so the question about was about parsing documents. Are we going to touch on parsing tables and figures, anything along those lines, or high level strategies to do this at least?
Yeah, so we will talk about parsing, all the different types of data that we'll cover in this course. If you want to talk more about specific parsing strategies, then definitely join any office hours and we can talk about those. Generally, this is not going to be an out-of-the-box solution if you're trying to parse very, very complex, different types of data. But I would recommend trying out of the box the tool called Llama Parse. We'll throw it in the chat here. That is probably the leading tool that you should try to see if it works for your use case and kind of go from there. Llama Index has some really great tooling to sort of look at structured and unstructured data. We got similar questions about multimodal stuff before. Any other burning questions? Cover Kenny here in the chat. Is there a specific day when we should start working on our demo day project? You should start working on your demo day project definitely by the midterm. We're going to force you to. You don't have to worry about it until about 3 weeks in. I'll remind you again. But next class, actually, I'm going to cover quite a bit on use cases. I'm going to make you think about this more. It's going to be part of the spinning up. We got to get to RAG. We got to get to prompting. You guys know enough to sort of put together a quick prototype. We're going to talk end-to-end prototyping next time and start thinking about our demo day projects. And then we'll talk more and more about how we can kind of, but when it comes to teams, start trying to meet people now. Start trying to find people that you're interested in working with now. Start thinking about people in your breakout room. It's a great weekend to try to say, hey, you want to have a quick one-on-one, grab a quick virtual coffee, just, try to chill, meet each other, learn a little bit more about what you're doing, what you're interested in. I kind of liked your vibe in the breakout rooms, and kind of go from there. This is a great time to start doing it. I'm glad you brought it up. And if you have other questions, please join us for office hours, but we're 1 minute over. Thank you for joining us, everybody, for week 1 of the AI Engineering Bootcamp Cohort 5. We've had an absolute pleasure serving you through week 1. Next week, we will cover end-to-end prototyping. We'll talk use cases. We'll cover LangChain. Week 3, we go agents and multi-agents. Week 4, we're into evaluation and synthetic data generation. It's going to be a blast, guys. We look forward to this journey with you. We hope you enjoyed week 1. We'll see you in office hours and on Discord in the meantime. Have a great evening, everybody. Bye, guys. We'll see you on Tuesday.
Bye, everybody. Have a great weekend. See you Tuesday.
Thank you.
Bye, guys.
Greg and the Wiz, if you got a second, I got something to show you.
Oh, you got something to show us. Yeah, let's go.
Can I screen share?
Yeah. Take the screen. Let's do it.
Do it, Nick.
Okay.
It's good to see you.
Good to see you too. So I'm working right now. This is a build, ship, share, a big one.
Let's go.
I'm working on a white paper with the head of AI for startups at Microsoft, basically on RAG and the future of intelligent applications. It's basically if you're an enterprise buyer and you've failed to set up agentic RAG or any complex kind of Gen AI application, it's probably for one of 8 reasons here. We have 8 startups that are building infrastructure to help solve all these problems. And so we're basically like, hey, what is a Gen AI native application? If you basically compress and abstract away these domain spaces of problems, it's context, building trust from the user, and then ultimately having production-driven development. And then interviewed, Jerry from Llama Index and Brian from Unstructured and Cody from Coactive, Labelbox, Ragus, Orcus, Contextual, Vectara, and then basically, how do you build not just answer engines, but action engines? And so a lot of this stuff is from you guys, planting the seed a year ago, and me been working on this actually since basically March of last year. So hopefully we'll just get this out through all of kind of Microsoft's kind of channels there and my firm's channels there. But would love to give you guys like the advanced copy or the pre-read just to make sure nothing I say is too dumb.
Yeah. Definitely send it over, dude. And maybe there's some sort of like cool event we could do around it, sort of talk about the problem space. And actually Rob came to a bunch of the demo days we did at Fourth Brain.
No way. Okay.
Yeah, dude. So like you
That's
should put
awesome.
that bug in his ear. Maybe he should come to this one and and serve as a judge. But I know he's a busy guy, but
but it's like, or hey, I mean, I know the attendees of the class, there are people that are like, maybe came from the traditional production engineering sides or at like large Fortune 500 enterprises that have, been trying to build this and scale it. It's like, hey, we could maybe have like, Jerry or like Brian or, some like 1 or 2 of the founders from that paper be like, hey, let me sell into Oracle or sell into, some other large enterprise here by saying like, these are the people in this boot camp that are building. They could build using Llama Parse, right? They could build using Unstructured API. They could build using, Ragus, right? So it could be a cool, community collab there for sure.
If you've got some motivation to sort of spearhead that a little bit, I mean, we're super close with the Llama Index guys and the Ragus guys. But, if you want to bring other folks in and sort of we can get people pumped around, that midweek midterm and sort of say, maybe we could even get some sponsor, like, hey, you use this tool, best tool use, $1,000 kind of thing. That could be super cool.
Yeah. Okay.
Thanks for sharing,
Definitely
dude.
send it over. Yeah,
Sure.
that's super hype. I mean, that's good work and excited to read it.
Yeah, it's looking good, man. It's looking good.
Awesome stuff. Okay.
All right,
We'll
dude.
see you guys next week. Cheers.
Have a good weekend. Bye.